Have you ever really thought about how we measure the world? I mean, it seems so simple, right? You grab a ruler, a tape measure, and you're good to go. But what if? What if everyone's ruler was a different size? Let's dive into that on a journey that, believe it or not, starts with a new school uniform and ends with the basic laws of how everything moves. So meet Deepa. She's got a new school uniform, but it needs a little tweaking. Her mother tells the tailor to make it longer by 4 angula, or 4 fingers width. It sounds like a simple, ancient instruction, right? But it's actually hiding a really big problem. And there it is. That's the million-dollar question, isn't it? Are we talking about her mom's fingers, the tailor's fingers, Deepa's? This one little instruction just blows the doors wide open on why we desperately need rules for how we measure things. And this brings us right to our first big idea, what I like to call the handspan problem. It's what happens when you try to agree on something, but everyone is literally using their own personal and totally different ruler. How can you get anything done? So, taking a cue from Deepa's uniform story, she and her friends decide to run a little experiment. The goal? Measure their classroom table. And their tool of choice? The belisht, or what you and I would call a handspan. You stretch your hand out, thumb to pinky, and go end over end. Seems easy enough? And check this out. This is where it gets really interesting. Look at their results. Hardeep measured 14 handspans. Padma got exactly 13. And Tasneem got a little bit less than 13. They all measured the exact same table, but every single one of them got a different answer. Why? Well, it's obvious, right? Their hands are all different sizes. What their experiment really highlights is the whole idea of a unit. You need a unit for any measurement. But the problem they ran into is that their unit, the handspan, was all over the place. To get the same answer, you need a unit that's the same for everybody. And that, of course, leads us to the solution, the hunt for a universal ruler. This wasn't just a problem for some kids in a classroom. Humanity struggled with this for centuries. If my foot is bigger than your foot, how do we trade fabric? How do we build a house? We had to find a better way. And the big breakthrough idea is this, the standard unit. Unlike a handspan or a foot, a standard unit is the same for everyone, everywhere, every single time. It doesn't matter if you're in one country or another, you get the exact same result. And that changes everything. So to make this a reality, countries all over the world actually got together and agreed on one system. It's called the International System of Units, or SI units for short. And for measuring length, the champion, the universal standard they all shook on, is the meter. And here's the beautiful part. The meter isn't alone. It's part of a family. For really long distances, like a highway, you've got kilometers. That's just 1,000 meters. For everyday stuff, you use the meter, or maybe a centimeter, which is just 1/100th of a meter. And for teeny tiny things, you've got millimeters. It all just works. It scales up and down perfectly. Okay, so we've got our standard unit, the meter. We've got our meter scale. Problem solved, right? Well, not quite. Turns out, having the right tool is only half the battle. You've got to know how to use it right. So here are 3 quick pro tips. First, your scale needs to be right up against the object you're measuring, flat as a pancake. Second, and this is a big one, look straight down at the mark. If you look from an angle, you get something called parallax error, and it can totally throw off your reading. And third, hey, if the 0 mark on your ruler is all busted, no big deal. Just start at the 1 centimeter mark and then remember to subtract that 1 from whatever you measure. Easy. All right, so we've totally mastered how long. But that's only part of the story when we're describing the world. Now we've got a new question to tackle. Not just how long something is, but where it is. And for that, we need a whole new tool in our toolkit. So let's check back in with Deepa and her friends. They're having an argument. Which is closer, the garden or the school? Half of them are convinced it's the garden, the other half are positive it's the school. So who's right? Well, here's the thing, they all are. Because each of them was thinking about the distance from their own house. And that's exactly why they couldn't agree. To talk about location, you have to have a shared starting point. We call this a reference point. It's the fixed spot on the map that everyone agrees is 0. It could be a bus stop, a city, or the starting line of a race. Without that shared reference point, you're just guessing. Here's a perfect real-world example. So Padma's on a bus, and she sees a sign on the highway that says Delhi 70 kilometers. What does that actually mean?
It means that her position, at that exact moment, is 70 kilometers away from the agreed-upon reference point, which is the city of Delhi. That sign would be totally useless without it.
Okay, now we can put it all together. We have standard units, like the meter, to measure distance, and we have reference points to describe location. With just those two ideas, we can finally start to speak the language of motion.
So here's the big definition. An object is officially in motion if its position is changing over time. And here's the crucial part, with respect to a reference point. So Padma on that bus wasn't just moving, she was in motion relative to Delhi. See how it all connects? Now, of course, things move in different ways. Let's start with the simplest type, linear motion. It's really just a fancy term for moving in a perfectly straight line. Think of a soldier marching in a parade or a car cruising down a long straight highway. Just point A to point B.
But what if you're not going straight? If your path is a circle, like a horse on a merry-go-round, you are in circular motion. You're moving, you're constantly changing direction, but you're always staying the same distance from the center point.
And finally, we have oscillatory motion. This is any kind of repetitive back and forth movement around a fixed spot. A kid on a swing is the classic example, right? But it's also the vibration of a guitar string after you pluck it. It's motion that just keeps repeating itself.
So let's wrap it up with a fun little challenge for you. Think about a roller coaster. It's basically a masterclass in motion, right? It uses all three types. So as you watch this ball travel along the track, where do you see it moving in a straight line? Where is it in circular motion? And could you maybe even spot moments of oscillatory motion? It's pretty amazing. We went from a simple finger's width to the physics of a roller coaster. Once you get the rules, you can describe how anything in the world moves.